Hi, welcome back to Calculus. Today's lesson is called Integration of Rational Functions by Long Division. When you have a function that is a fraction and the degree of the numerator is either equal to or greater than the degree of the denominator, and by that I mean the highest exponent that appears would be the degree, then you can solve the problem by what's called integration by long division. And I have 4 examples that I'd like to show you of this process. Example number 1 is the integral of 3x plus 4 over x plus 3 dx. And this would be a candidate for integration by long division because the degree of both the numerator and the denominator is 1. They're equal degrees. So we're going to divide x plus 3 into 3x plus 4. And when we do this, we only look at the first terms of each of the 2 binomials. I need to see what I would have to multiply x by to get 3x, or in other words, how many x's divided into 3x, and that would be 3. So when I do long division, I multiply downward. 3 times x is 3x. 3 times 3 is 9. And I always want to subtract the bottom polynomial from the top polynomial. So when I subtract, this is going to become negative, and so is this. And I get 3x minus 3x, which is 0. 4 minus 9, which is negative 5. Just as when I do regular long division with numbers, if I have a remainder, it gets put over the divisor. So I take this negative 5 and I write minus 5 over x plus 3. I'm now going to rewrite my original integral as this answer that I got for the quotient. So I have the integral of 3 dx minus, and I'm going to factor the 5 out in front, 5 times the integral of 1 over x plus 3 dx. I broke it up into 2 parts just because one part wasn't a fraction, the other part was. Then I just use my antiderivative rules. The antiderivative of 3 is 3x. And the antiderivative of 5, integral of 1 over x plus 3, this is an ln case. The integral of 1 over x would be ln of the absolute value of x. So this will be 5 ln of the absolute value of x plus 3 plus c. The second example is the integral of x cubed minus 3x squared plus 5x minus 3 divided by x minus 1 dx. Again, this is going to be a candidate for integration by long division because the degree of the numerator in this case is higher, it's 3, compared to the degree of the denominator, which is 1. So once again, I'm going to do long division. X minus 1 divided into x cubed minus 3x squared plus 5x minus 3. I'm only going to look at the first terms of each one, so x goes into x cubed, x squared times. You can either divide the x out of the x cubed to get that, or just figure out what would you multiply by x to get x cubed and the x squared. It gets multiplied by each of the 2 terms of the binomial, so I get x cubed minus 1x squared. But again, when I'm doing long division, I want to subtract the lower polynomial from the upper polynomial. So this becomes minus, this becomes plus. We just switch the signs because we're distributing a subtraction sign. And we get negative 2x squared. Just as I do in long division with numbers, I bring down the next term, which is 5x. And I repeat the process again. X times negative 2x would give me negative 2x squared. I'm going to now multiply that by the x and multiply the negative 2x by the negative 1, which gives me positive 2x. And once again, I subtract, so I'm going to change my signs to their opposites, and I get 5x minus 2x, which is 3x. And once again, the negative 2x squared and the positive 2x squared add to 0. I bring down my last term of negative 3. X times 3 would be 3x. That'll be plus 3. 3 times x is 3x. 3 times negative 1 is negative 3. When I change my signs to their opposites, I get a remainder of 0, which means that this trinomial divided by, this 4-term polynomial divided by this binomial divides out perfectly even without a remainder. So I can now rewrite my entire integral as the integral of x squared minus 2x plus 3 dx. The antiderivative, if I add 1 to the exponent, I get x cubed over 3 minus 2x squared over 2 plus 3x plus c, and the fraction for the second term can be simplified so that I get an answer of x cubed over 3 minus x squared plus 3x plus c. Example number 3 is another candidate for integration by long division because the degree of the numerator is 3, the degree of the denominator is 2. This one is going to be a little bit different in the setup of the long division because you're going to see that we need to put in any missing terms that we have for either of the polynomials in the top and the bottom. And let me explain. The bottom polynomial has an x squared term, but it's missing an x term. So I'm going to write the bottom polynomial as 2x squared plus 0x plus 1. The polynomial in the numerator is just an x cubed, but I'm going to also put in the ones that are missing as I count my way down to a constant. I'm going to put plus 0x squared plus 0x plus 0. So it's very important that if you're missing a term as you count down from the highest exponent down to the constant, that you put those terms in as 0 terms. And it actually doesn't matter whether you put plus 0x squared or minus 0x squared. It would have the same effect when we do our division. So I start by dividing 2x squared into x cubed. And right away, you're going to notice that 2x squared is going to go in a fractional amount of times. So I'm actually going to adjust this a little bit. This is normally how I would set it up, but I'm going to rewrite my original problem so that I have the same constant on the top as the bottom. In order to do that, I'm going to need to multiply the top by 2, which means I'm going to put a 1/2 on the outside. So I'm going to put 2x cubed over 2x squared plus 1 dx, and notice again that I have the 1/2 on the outside to counteract the 2 that I put on the inside. We'll worry about the 1/2 later. So let me go back to what I was doing earlier. I'm going to put 2x squared plus 0x plus 1 divided into 2x cubed plus 0x squared plus 0x plus 0. This will make it a lot easier just because I don't have to put fractions in my divisional answers. I can put whole numbers instead now. So 2x squared goes into 2x cubed x times. X times each of these 3 terms is going to give me 2x cubed plus 0x squared plus 1x. And I'm again going to subtract, so I put a minus sign on each one, and I end up with everything dropping out except for a negative x. And I do have that plus 0 on the end, but I'm not going to need to use it because if my degree is already lower in my remainder than it is in my divisor, and in this case it's a 1, my divisor has a 2, I can immediately now just take that and make it a mixed number as part of my answer. So I'm going to put minus x over, and the original expression here was 2x squared plus 1. I now rewrite my integral as, and don't forget about the 1/2, so we have 1/2, the integral of x dx, that's the first part, minus the integral of x over 2x squared plus 1 dx. And I'm going to move the long division out of here just so I have a little bit more room to work. So you'll notice that this over here, I don't have a constant that I can just pull out in front. I have a variable, but if I let u be the denominator, then du is the derivative, which is 4x dx. And all I'm going to need is a 4 with the x and a 1/4 on the outside to fix this. So I'm going to put that in there. I have a 4x and a 1/4. Let me squeeze that in there. And I can rewrite this now as 1/2 integral of x dx. We'll deal with that in a minute. Minus 1/4. And this 4x is part of the du. So it's just going to be the integral of 1 over u du if I use u substitution there. Taking the antiderivative now, I have a 1/2 on the outside still. Antiderivative of x is x squared over 2. And this is an ln case, so I'm going to have 1/4 ln of the absolute value of u. And to finish up, I just need to distribute the 1/2 through the quantity, and I end up with 1/2 times x squared over 2 would be x squared over 4 minus 1/2 times 1/4. I'm going to just write that as ln of what u really was, which was 2x squared plus 1. And by the way, that can't ever be negative, so I can just put parentheses if I want. All over, and I took 1/2 times 1/4, so that would be all over 8, and then plus c. The fourth and final example is also a candidate for polynomial long division because I have a degree of 3 in the numerator and a degree of 1 in the denominator. So I'm going to divide x plus 2 into, and once again, try not to forget to put the missing terms in. You have to have every term starting with the highest exponent down to the constant. So this will be x cubed plus 0x squared plus 0x minus 1. X divides into x cubed, x squared times, multiply downward. Subtract the bottom binomial from the top one, so this becomes minus, this becomes minus. I get negative 2x squared. Bring down just my 0x. Because of the fact that there's a binomial here, I want to have a binomial here as well. X times negative 2x would give me negative 2x squared. Negative 2x times x is negative 2x squared. Negative 2x times positive 2 is negative 4x. But I'm going to subtract, so I'll change the signs to their opposites, and I get 4x. Finally, I bring down my minus 1. X goes into 4x 4 times. 4 times x is 4x. 4 times 2 is positive 8. But because I'm subtracting, I'm going to change these signs to their opposites, and I get negative 1 and negative 8, which is a remainder of negative 9. And I'm going to make a mixed fraction out of this and just put minus 9 over the divisor, which is x plus 2. So I'm now going to rewrite my integral as the integral of x squared minus 2x plus 4 dx. And once again, I'm just going to make a little bit more space here. Minus, and it was 9 over x plus 2, so I'm going to write that as 9 times the integral of 1 over x plus 2 dx. I'm not going to have to use u substitution this time because my denominator was already linear, so its derivative would just be 1. If it wasn't linear, you would have to use u substitution before you could use the ln case. However, in this case, if I take the antiderivative, I get x cubed over 3 minus 2x squared over 2. Remember, when you take antiderivatives, you add 1 to the current exponent and divide by that new exponent. Plus 4x minus 9, and it's 1 over u, which is going to be the ln of the absolute value of x plus 2, plus c. And once again, I can simplify a little bit, cancel out the 2's, and end up with a final answer of x cubed over 3 minus x squared plus 4x minus 9 times the ln of x plus 2 plus c.